Today we'll talk about tenfold classification of materials. Basically these are done for the insulators and the superconductors, and these tenfold classification dates back to 1996-97 by Altland and Zeinbauer. In fact, you can see a very nice lecture by Altland in Topological Matter School in 2017. And so we will not get too much into details of this classification, but we'll tell you the basic things based on the discussion that we had so far on these time reversal and particle hole and other symmetries that we talked about. So we'll start with this two main symmetries that we have learned. One is called as a time reversal symmetry, which of course means that t going to minus t and so on, and what it means is that if a particle is made to move with a velocity v in the opposite direction, that is with a velocity minus v, whether the physics remains invariant or whether the Hamiltonian remains invariant. And we have elaborately seen the consequences of such time reversal symmetry being present or absent. Especially if they are present, then one has these Kramer's doublets, which we have done. Now also we have looked at the particle hole symmetry, and this is has been talked about when we discussed Kitaev chain and so on. So whether a particle becoming a hole and so on, whether that has a bearing on the Hamiltonian, and if it does, then of course there are these energy E corresponding to a particle will have an energy minus E corresponding to a hole, and so on and so forth. Okay, so if you want a sort of pictorial representation of that, so let me sort of draw a conduction band and the valence band. So this is the CB and the VB, and we create a hole here. So there is a single hole excitation here, and this will correspond to a single particle excitation here. Okay, and of course this is your Fermi energy. Let me draw it with a color. So this is Fermi energy, and this is for E greater than EF, and this is for E less than EF, and so on. Okay, so this is really the particle hole symmetry that we talk about. So there is a corresponding to an energy minus E for a hole excitation, there will be a particle excitation at an energy plus E, and so on. Okay, and in terms of a band picture, we can do it. Suppose we take a cosine band, and we fix the Fermi level somewhere here, and then the particle hole symmetry would correspond to something like this. So there is a k minus pi will correspond to for a particle will correspond to a hole at these k. So say this is some ak minus pi, and this will be some ak dagger, and so on. So this is the the hole, and this is the particle, and so on. Okay, so we have also learned that the time reversal symmetry, which we write it by T, and the particle hole symmetry, which we will write it by C. And the reason that we write it by C usually because traditionally this particle hole symmetry is denoted as a charge conjugation symmetry. Okay, it's called as CCS, and I believe that the people who work in high energy physics, they use this term more often than the people in condensed matter physics. So this is called charge conjugation symmetry, and that's why it's written with a C. So this T and C are the ones that we are going to talk about, and we have in various situations we have talked about how T acts on a Hamiltonian which is of the form of a Dirac Hamiltonian, say D dot sigma, and then how T acts on each of the components of D and how the Hamiltonian gets transformed. We have done that elaborately in the context of when we did the SSH model and the Kitaev model. So this T has a form which is, we know that it has a form like a K conjugation. It's also usually written with a UK, where U is a unitary operator and this K is the complex conjugation, and it makes it a anti-unitary operator, and both C is also an anti-unitary operator. Now this is for spinless fermions or spinless particles. And we have also looked at how in presence of spin this is not enough to represent the symmetry. It's written as I sigma yk for the spinful particles, and we have seen this earlier. Okay, and this sigma y is nothing but the y component of the Pauli matrix, and this can be operated on a given term of the Hamiltonian, and then term by term we have talked about how these Hamiltonian or rather how this symmetry operation transforms. So now this T is equal to the square of this is equal to +1 for spinless particles and so on. Okay, I'm just trying to remind you of all the properties that we have done, and this is equal to -1 for spinful particles. Okay. Similarly, P also has this, so P square is equal to +1 and -1 as well. So just like whether you do the particle hole transformation twice, it will either give rise to a minus sign or it will give rise to a plus sign, that is +1 or -1. And so both T square and P square have values which we have learned so far is equal to ±1. Now it's also true that a system not having time reversal symmetry or not having particle hole symmetry should also have these values for this T square and P square, and in that case the trivial cases where there is no time reversal symmetry or there is no particle hole symmetry, then we write it as T square and P square equal to 0. So now you see that T square has all these three values, so it's +1, -1 and 0, and P square has a +1 and -1 and 0. Okay, so if you put together all the combinations, so we can have consider that T square equal to +1 and P square +1, -1 and 0, and then T square -1 and P square equal to +1, -1 and 0, and similarly for T square equal to 0, P square equal to +1, -1 and 0. So there are of course 9 sort of these things present, I mean 9 types that are present. Okay, so 9 types coming from the 3 cross 3. Okay, so 9 values for these T square and P square based on these +1, -1 and 0, they are present in the system, but we have talked about a 10-fold symmetry classification of materials, and this 10th one is really coming from another symmetry which is called as a chiral symmetry, which we have seen as well in certain situations. And this chiral symmetry is nothing but let's write it with S, and this S is nothing but it's a product of the PT symmetry. And now this S does not have values +1, -1 and 0, but S has values which are 1 and 0. Okay. Now it can happen, or rather the 10th classification is coming from S equal to 1 but P and T equal to 0. Okay. So for systems with chiral symmetry, so let me write it with only chiral symmetry. Okay. And this only is important here because T and P are equal to 0. So this, so S is equal to 1. So that is the 10th type of system classification that we have. Okay. So we have all these things, all the 9 combinations that we have talked about, and the last combination is P equal to T equal to 0 and so on. Okay. So this chiral is not a trivial symmetry that we can understand just like we have understood the time reversal symmetry or the particle hole symmetry. In fact, the chiral symmetry is very apparent in systems with sublattice structure. For example, you have seen graphene. Graphene has a sublattice structure. The unit cell consists of 2 atoms. There are 2 atoms in a given unit cell, and they are called as A and B atoms, and there is an inversion symmetry with respect to the bond, the perpendicular to the bond that connects. So what I'm trying to say is these is the structure, and so this are, so these are A and B. So if you draw a line here, then you can change or you can invert between about this red line, and A becomes B and B becomes A. Now since both A and B correspond to carbon atoms in graphene, so that's how it is having a sublattice symmetry, and same that it goes with the SSH model. So the chiral symmetry is a sublattice symmetry for systems with sublattice. So chiral in certain systems. Okay. And which systems? The systems that have these sublattice structure. Okay. So that's how physically you may want to understand how this classification comes about. Okay. So let me look at the table that sums up this 10-fold classification. Now you see that T is the time reversal symmetry, C and then S. So S is chiral. So let me write it. T is time reversal. Once again, C is particle hole or charge conjugation. So we can write both or charge conjugation. And S is chiral. Okay. And you see that there are these time reversal symmetry being there. So the 1 means that it is there. So it's either 1 or -1. So that's how it is classified. So 1, 1 and 1. So that corresponds to the BDI class. So this BDI that's there. Then if it's +1, -1 and 1, it's called CI, and then it's AI, and then it's B3. C2, A2, D, C, A, A3 and so on. This is the last class, the 10th class, where T is equal to 0, C is equal to 0. That's these two symmetries are not there. It's not invariant under these time reversal or the charge conjugation symmetry, but still the system has a chiral symmetry, and that's called as a A3 class. Okay, so these are all these names that are proposed. So there's BDI and CI or C1, A1, B3, C2, A2, D, C, A and A3. Okay. So, all our materials including the insulators and the superconductors will fall into one of these categories, and they are sort of based upon these values that you see appearing at the columns corresponding to T, C and S. Okay. S is nothing but a product of T and C. So, this is the tenfold classification of materials. Of course, I am presenting a very concise version of this classification that is only relevant to us, and will not go any farther than that. Okay. So, now of course, we get these symmetry classes, but then we have to talk about the topological invariants as well, so that we know that which topological invariant we are talking about, and we have learnt about a number of topological invariants. So, for example, in SSH model and Kitaev model, we have seen that the topological invariant is the winding number. Okay. There are, people talk about Zuck phase and so on, but all these are related to the winding number. For example, even in systems where all of dx, dy and dz are present, so that winding is a difficult thing to visualize, or winding about some particular point in the Brillouin zone is difficult to visualize, and then one talks about Berry phase, which is nothing but the line integral of the Berry connection over the Brillouin zone. Okay. So, it's winding number there. So, the topological invariant is the winding number. For example, we have talked about 2D electron gas in presence of a magnetic field, and then we have talked about this, and then the Hall conductivity is expressed in terms of this Chern number, and same that goes with the Holden model. So, by and large, whenever there is a Hall effect, quantized Hall effect, there has to be a Chern number, which is the topological invariant. So, the Chern number sits right in front of the E square over H, and this C takes values which are 0, 1 and so on. Okay. Now, there are something more to this. I mean, there are these Z invariant, or there are Z2 invariant. Okay. And these Z and Z2 invariants are based upon whether Z invariant, the Chern number is a Z invariant. What it means is that it can take values like 0, 1, 2, 3, 4, etc. And so, that is integer classification. So, this is an integer classification. And this is of course binary 0 and 1. Okay. So, 0 correspond to the trivial phase, and 1 corresponds to the topological phase. So, these two are the main topological invariant that one talks about. You see, Z can take values 0, 1, 2, 3, any value in principle. Z2 cannot take any value. So, if you think of winding number, then winding number is really a Z invariant, because it can take values 1, 2, etc., or 0, 1, 2 of course. And so, it depends on how many times you wind the origin as you take K from over the Brillouin zone, entire Brillouin zone. You have to do it again in order to have another winding, and so on and so forth. Okay. The Z2 invariant of course is the quantum spin Hall insulator that we have seen recently. Okay. So, this is quantum spin Hall insulator. Ken-Milly model is this corresponds to the Z2 invariant. Okay. So, we need to identify the topological invariant that is important for a particular case, and that particular case will be decided by the symmetry of the Hamiltonian, that is whether the Hamiltonian has all of time reversal, particle hole and chiral symmetry, or it doesn't have one of them, it doesn't have two of them, and so on and so forth. Okay. So, the topological invariants are classified like this. So, this is only shown in dimensions 1, 2 and 3. Of course, in this particular case we have looked at only 1 and 2 dimensional materials so far. So, this is our domain so far. Okay. So, these symmetry groups are present here. So, there is a A3, A1, BDI and so on so forth. There are these the topological invariants are in 1D 0, which means that there is no topological invariance, it is topologically trivial. It does not have any topological properties. In 2 dimension it has the Z, which is a Chern number. A3 1 dimension it has Z, and 2 dimension it is 0 and so on, and then AI, BDI and so on and so forth. Okay. So, these are the topological invariants, and where are we interested in? We are interested in say for example, we are interested in the IQHE, that is integer quantum Hall effect or quantized Hall effect that we have studied, and if you look at that, that has no symmetry at all. So, it forms into the A class. Okay. So, it forms into the A class, which has no symmetry, it has no time reversal symmetry because of the magnetic field being present, and it has no charge conjugation symmetry. It is a completely disordered material, and there will be no chiral symmetry as well. So, it falls into the A class, which is here, and these A class, if you look at it here, then the A class has in 2D this is the Z invariant, and this is your IQHE, and the Z invariant is of course identified with the Chern number. Okay. What about the SSH model? So, the SSH model is here. So, so this is the SSH model and the Kitaev p wave chain with spinless fermions. So, this is SSH. Let us just write SSH to begin with. We will talk about the Kitaev. So, this is SSH. And what is the topological invariant? Is a winding number which is also a Z invariant, just like a Chern number. Okay. And we will just talk about the Kitaev in just a moment. Let us talk about the quantum spin Hall. So, quantum spin Hall effect, that is the Z2 invariant. You know very well that that is the. So, there is a Z invariant, there is a Z invariant, and that is a Z2 invariant, which we have discussed elaborately for a system with time reversal symmetry. So, that is A2. So, let us just go back and see what A2 is. A2 has a time reversal equal to -1. These are really the T square values. Okay. So, T square values, in fact, they are written TC, but they are the squares of this. This is -1 because of the reason that this is with a spin. So, with spin it is I sigma y into k, k being the complex conjugation, and it has no other symmetry. There is no particle hole symmetry, there is no chiral symmetry and so on. So, this falls into the A2 class, and if you go here, you see that the A2 class has a topological invariant, which is a Z2 invariant, and that is the QSH. Okay. So, now let us come to the Kitaev model. There is a dichotomy or rather there is an ambiguity present in this Kitaev thing. So, Kitaev, if we talk about the Kitaev chain with p wave superconducting correlations and we talk about spinless particles. Suppose we do not talk about electrons at all. So, we talk about spinless particles with p wave correlations, superconducting correlations. Then it falls into the BD1 class. Okay. It has same symmetries as the Kitaev model, and just to go back and forth. So, it is all of the symmetries being present, that is there is a time reversal symmetry, there is a charge conjugation symmetry, and then there is a chiral symmetry as well. Okay. So, it is the same thing as the BDI class, and then BDI class will be characterized in one dimension by a Z invariant, and which we saw that we have denoted the topological invariant as the winding number for that particular problem. Okay, but however, there is also true that if you talk about electrons, and then you have to talk about spin. Okay, and if you need to include spin, then you actually can talk about S wave superconductor. You don't need to talk about P wave superconductivity. You can also talk about P wave superconductivity, but you can talk about S wave superconductivity. But then you need to make a spin polarization in order to talk about only one kind of spin being there, and then there are these other things such as spin orbit coupling being present, etc. That's it is usually studied with S wave superconducting correlations. And then of course, because you need a magnetic field, there is no time reversal invariance, and then you're not really there, you are there in this thing where it's only particle hole symmetry because of the P wave superconducting correlations, neither chiral symmetry nor time reversal symmetry, and that's where you have a D class, and the D class is represented by a Z2 invariant. Okay, so this is so I'll write SSH and spinless Kitaev, and here spinful Kitaev. That's a D class, but you see that the topological invariant is Z2 and not equal to Z. So these are some of the things that we have discussed during the course, and in some of the cases there are we can write down the Hamiltonian as say for example H equal to D dot sigma and so on, and then in 1D, and then sigma denotes the Pauli matrices. They don't denote spin, but they denote other degrees of freedom. That's why sigma is sometimes called a pseudo spinner. And in sort of the quantum Hall effect, we have denoted with the Chern number, the topological invariant, and in for example SSH Kitaev, let's just stick to spinless particles at this moment. So we have done, and then we have done so this Z invariant, then these are winding numbers which are also Z invariant, and then we have done a quantum spin Hall phase which is actually the Z2 invariant. Okay, so this is in 2D, this is in 1D we have done, and this is again in 2D graphene that we have done. Okay, so there are various such classifications that exist. So if you look at the table and what symmetries are present in a given Hamiltonian, then you identify the symmetry class of the material, and from this table you can read out the topological invariant, and if you know how to calculate it, like for all these cases we have shown how to calculate the topological invariant, then you are more or less that's about the classification of materials. Okay. One last thing to talk about, there is something called a Bott periodicity, and you see that it's always written up till 8. Of course, we were now talking about 0, 1, 2, 3 or 1, 2, 3 dimensions. Now if you write it from 0 to 8, the Bott periodicity says that everything from the 9th dimension onwards it starts repeating. So the periodicity is from 0 to 8, these 9 classes. This again the same things, but of course in dimensions which are very large. These are of course you cannot have materials present in this like 4th dimension or 5th dimension, but they are mathematical dimensions which identify the different topological invariants, and it says that till 8 it it carries on, and then of course everything gets repeated from 9th onwards. So 9 is same as 0 and 10 is same as 1 and so on and so forth. Okay, that's called as a Bott periodicity. That's not very important for us, but what is important for us is to have a comprehensive understanding of a certain material, and if we can write down a Hamiltonian, then we should be able to know the symmetries of the Hamiltonian, and from the symmetries, just the simple symmetries of T and C, and of course another one which is a multiplication or a product of T and C, we know that which symmetry classification does the material fall in, and we can calculate the topological invariant, and that will tell you that whether the material has topological properties or it may not have topological properties. It may be a simple band insulator or just a normal superconductor, which is well known. But whether the edge modes or the surface modes, they contribute to the conductivity only or the transport properties only, in that case the material is supposed to be topological, otherwise it's termed as trivial.